Hello and welcome to this new series where we're going to talk about radio frequency engineering and microwave. Also, it will mainly focus on the Smith charge adaptation, but mainly around the Smith charge characteristic impedance, matching impedance, matching, evaluating the reflection coefficient, the VSWR, etc. First, fundamentals of electromagnetics. Description. This section introduces the fundamental principles of electromagnetics, which are essential for understanding the behavior of electromagnetic waves or EM waves in high frequency, which is a different behavior than in lower frequencies, RF systems or radio frequency systems, and microwave engineering. It covers Maxwell's equations, wave propagation, and the transmission of electromagnetic waves in various media. Maxwell's equations, conceptual overview. Maxwell's equations form the foundation of classical electromagnetics. They describe the relationship between electrical fields and electromagnetic fields, respectively E and B. Also, charges ρ and currents J, electromagnetic current. Gauss's law for electrical fields. So nabla E, which is the gradient or the derivative on different axes for the electrical field E, is given by ρ divided by epsilon 0, okay? Where epsilon 0 is the permittivity of empty space. States that the divergence of the electrical field is proportional to the local charge density, mainly. Gauss's law for magnetism. Gradient of B is equal to 0, which implies that there is no magnetic monopoles, okay? Magnetic field lines are continuous, which means that the derivative, which indicates the angle or the slope between the magnetic field vector and the axis, it is 0, meaning that there is no variation. The magnetic field lines are continuous. So there are no changes. That's why the derivative is equal to 0. Faraday's law of induction. Okay, so nabla cross E is equal to the minus partial derivative of B over T, meaning that it is equal to the partial derivative of the magnetic field tensor or vector in respect of time. So a time-varying magnetic field induces an electrical field. Quite simply placed or put, that the change of the magnetic field in respect of time, which is the minus partial B over T, induces or generates a time-varying electrical field as well. It changes the electrical field, which is classical electromagnetism. When you have a changing magnetic field around a conductor, it inducts an electrical field. It creates a current within the conductor. Ampere's law with Maxwell's correction. So the change of the magnetic field is given by mu0, which is electromagnetic permeability, multiplied by J, which is the magnetic current density, plus mu0 epsilon 0 again, it is the permittivity of the dielectric, which is empty space in such case, multiplied by the partial derivative of E, the electrical field, in respect of time, which is the change of the electrical field in respect of time. So a time-varying electrical field generates also a magnetic field in addition to currents. All right? Here, epsilon 0 is the permittivity of free space, mu0 is the permeability of free space. Rho is the charge density and J is the current density. Wave propagation in free space. Electromagnetic waves are solutions to Maxwell's equations. In a source-free region, okay, so rho is equal to 0, J is equal to 0, no current, no charge for free space. So nabla square E, which is the second gradient of the electrical field minus mu0 epsilon 0, second partial derivative of E, the electrical field intensity, over time is equal to 0. The same thing is for the second gradient of B minus mu 0 epsilon 0 second partial derivative of B in respect of time is equal to 0. These are the wave equations for electrical and magnetic field. The solutions are transverse electromagnetic TEM waves where E is orthogonal to B, orthogonal to K. With K being the propagation vector, the intrinsic impedance of free space is given by eta 0 is equal to the square root of mu 0 divided by epsilon 0, with mu 0 is the magnetic permeability of empty space, epsilon 0 is the permittivity also of empty space, approximately equal to 377 ohms. Frequency, wavelengths, and phase velocity. The frequency f, wavelength lambda, and phase velocity Vp are related by Vp is equal to f times lambda. The velocity of the wave is equal to the lambda of the wave multiplied by the frequency. For electromagnetic waves in free space, Vp is equal to C is equal to 1 divided by square root of epsilon 0 mu 0, which is 3 times 10 to the power of 8 meter per second. Why? Because in free space, okay, there is no deceleration of the speed of light. So there's no change or attenuation in the speed of light in free space, unlike an environment that has air molecules within it, okay, that would alter the speed of light. Time harmonic plane waves can be expressed as ERT is equal to E0, which is the intensity of the electrical field, times E, which is the exponential j omega t minus kr. Omega is the angular frequency, which is equal to 2 pi f. BRT is equal to also B0, intensity of the electrical field, E exponential j omega t minus kr. All right? So this is the change of the magnetic field in respect of time is equal to B0, which is the original intensity of the magnetic field, the same thing for the electrical field, of course, times E exponential j omega t minus kr. R would be the distance from the source. Transmission of electromagnetic waves in media in a place that is not empty space, through a cable, through a dielectric, whatever. When electromagnetic waves propagate through a medium with permittivity epsilon, permeability mu, and conductivity sigma, the wave equation becomes nabla square E, which is second gradient of the electrical field, minus mu E, instead of mu 0 epsilon 0, second partial derivative of the electrical field in respect of time, minus mu sigma partial derivative of the electrical field in respect of time is equal to 0. The propagation constant gamma in a lossy medium that has loss and attenuation is given by gamma is equal to alpha plus j beta is equal to the square root of j omega mu multiplied by sigma plus j omega epsilon. Alpha is the attenuation constant, and beta is the phase constant in radian per meter. The phase velocity in the medium is given by Vp is equal to omega divided by beta, which is the phase constant, is equal to 1 divided by square root of mu epsilon. For lossless media, sigma would be equal to 0, so there would be no conductivity, which would generate a lossy current. Finally, electromagnetics forms the foundation for understanding high-frequency wave behavior. Maxwell's equations, wave propagation, and material interactions are crucial for designing antennas, transmission lines, and microwave circuits. Second chapter, transmission line theory. Transmission line theory studies the behavior of electrical signals when the physical dimensions of the circuit are comparable to signal wavelengths. At high frequencies, conventional lumped circuit models fail. Why? The reason is that the conductor, the medium where the wave is traveling, okay, such as a wire, a copper wire, would start behaving as an inductance, a capacitor based on the length of the conductor in comparison to the length of the wave. Okay, so when the wavelength is almost the same as the length of the conductor or the circuit, okay, the circuit would start behaving in an unconventional way. So it would start behaving such as an RLC circuit, okay, a condenser or capacitor, an inductance. So it would act as an electronic component having a magnetic field on the inside. So at high frequencies, conventional lumped circuit models fail and distributed effects must be considered. Lumped versus distributed systems. Lumped systems and low frequency circuits, components such as resistors, capacitors, and inductors are assumed to be localized lumped. Okay? The circuit dimensions are much smaller than the wavelengths. That's the difference. So the dimensions of the circuit are much smaller than the wavelengths, than lambda. So L would be a lot lesser than lambda. Thus, voltage and current are assumed uniform across the entire components. They won't change. Meanwhile, for distributed systems at high frequencies where the length would be approximately or would become approximately equal to lambda, so the length of the conductor becomes approximately equal to the wavelength traveling the conductor, voltage and current vary along the transmission line in such case. The electrical properties are distributed continuously along the line. They would change, requiring a different modeling approach. Transmission line parameters R, L, C, and G, where R is the resistance per unit length, accounts for conductor losses. L is the inductance per unit length. Henri per meter represents magnetic energy storage. C, capacitance per unit length. Farad per meter also represents electrical energy storage. Okay. And finally, G, which is the conductance per unit length. Siemens per meter, accounting for dielectric losses. These parameters form the distributed equivalent circuit model. Telegrapher's equations. The voltage Vxt and current Ixt along the transmission line are governed by the telegrapher's equations. By the way, Vxt is the voltage in respect of distance from the source and time. Same thing for the current, changes in respect of distance or position and time also. Now, the voltage or the change of voltage in respect of distance here, partial derivative of V in respect of x, is equal to minus Ri, which is voltage, by the way, xt. So R is the resistance and I is the current, minus L, partial derivative of Ixt over time. So it is the inductance times the partial derivative of the current in respect of time. Now, partial derivative or the change of current in respect of the distance is equal to minus GV, G being the conductors, times the voltage in respect of x and t, distance and time, minus C, partial derivative of V, the voltage in respect of time. So both of them, okay, here is the voltage times the capacitance, okay, the change of voltage in respect of time times the capacitance, and with the conductance here times the voltage would give us the change of current in respect of the position. In the phasor frequency domain, assuming E, j omega t dependence, so partial derivative or derivative of V in respect of x is equal to minus R plus j omega L times I. Derivative of I in respect of x is equal to minus G plus j omega c times V. Wave equations. Combining the telegrapher's equations yields wave equations. So second derivative of voltage in respect of position is equal to gamma square times V, where gamma again is alpha plus J beta. It is the propagation constant. And derivative of the current in respect of the position gives us gamma squared times I, where gamma is the propagation constant. The general solutions, so Vx is equal to V plus E minus gamma x plus V minus E gamma x. Ix is equal to V plus over Z0 E minus gamma x minus V minus over Z0 E gamma x. By the way, V plus is the incident voltage, incident wave. Okay, so when you are feeding from a source, you are feeding a resistance or a charge. So you have a signal, unlike classical circuits, you have a signal that goes, okay, but it might not completely dissipate within the charge. So you would have a reflective signal that goes in the opposite direction. That can create a standing wave ratio. That would be V minus, which is the part that's being reflected from the charge, especially if the charge is not completely adapted, meaning that it doesn't have the same adaptation impedance. And we're going to get to that. Ix also is equal to V plus over Z0 E minus gamma x. Gamma is the propagation constant, implying that it's a wave traveling from the source to the charge, and minus V minus over Z0 E gamma x. V minus is the reflected wave. The propagation constant gamma is defined as gamma is equal to alpha plus J beta is equal to alpha is square root, actually, yeah, it is R plus J omega L, square root of those two. So R plus J omega L corresponding to alpha, and beta is G plus J omega C. Alpha is the attenuation constant, and beta is the phase constant, the phase of the wave. Characteristic impedance Z0. The characteristic impedance of a transmission line is the impedance at which we need to adapt different components so as to remove the losses. Okay? This is how much important it is in order to remove or to reduce the losses and the reflection from the load or the charge, that would be an antenna at the edge of a transmission line, and the source, which is the feeder of that antenna. Z0, or the characteristic impedance, is given by the square root of R plus J omega L divided by G plus J omega C. L inductance, C capacitance, R resistance, and G conductance, which is the inverse of resistance. It represents the ratio of voltage to current for a traveling wave along the line. So Z0 is equal to the ratio between voltage and the current that are both incident. Okay, so V plus divided by I plus. Now, for an ideal lossless transmission line, there would be no resistance and no conductance. In other words, the resistance would be zero, and the conductance of the line would be also null. Thus, gamma becomes equal to J beta, is equal to J omega square root of LC. So Z0 becomes square root of L divided by C. The inductance divided by the conductance. Beta becomes equal to omega square root of LC when you have an adapted line. The wave velocity is given by V is equal to omega divided by beta equal 1 divided by square root of LC. The opposite of that would be a lossy line, where you would have values for the resistance and the conductance. They would be different than zero. Propagation constant in such case becomes complex. So gamma is equal to alpha plus J beta. Approximation for low loss lines, R would be so much lower than omega L, and G much lower than omega C. Alpha would be approximately equal to R divided by 2 square root of C over L plus G over 2 square root of L over C. Beta approximately equal to omega square root of LC. Finally, as a summary, at high frequencies, circuits must be modeled as distributed systems. Transmission lines are characterized by RLCG, resistance, inductance, capacitance, and conductance. Signal propagation is governed by the Telegrapher's equations. Key quantities include propagation constant gamma, characteristic impedance Z0. Lossless lines simplify analysis, while lossy lines introduce attenuation, damping. Chapter 3, Reflections and Standing Waves. Description. When a transmission line is terminated with a load impedance different from its characteristic impedance, which is Z0, part of the incident wave or signal would be deflected or reflected back from the charge. Why? Because it's not being fully or entirely consumed by the charge. That would be an antenna at the edge, for example. So a part of the signal would bounce back in the direction of the source because it hasn't been completely exhausted or consumed by the charge at the end or the termination of the line. This section analyzes reflections, standing waves, which is when the signal going, it bounces back, forms like a flipped two sine waves, okay, just like nodes, sequential, okay, that would be the VSWR, variable standing wave ratio, and power transfer in transmission lines. First, the reflection coefficient key. Reflection coefficient quantifies the ratio of the reflected wave over the incident wave, okay, which is basically the amplitude of the reflected over the amplitude or magnitude of the incident wave at the load. So key is given by V minus the voltage of the reflected wave divided by that of the incident wave, V minus over V plus. In terms of impedances, key is equal to ZL minus Z0 divided by ZL plus Z0, where ZL is the impedance of the load or load impedance, and Z0 is the characteristic impedance to which we need to adapt the line, or rather the load. Special cases, when we have matched the impedance of the load to the characteristic impedance of the line, which means that ZL is equal to Z0. In such case, there would be no reflection, so key would be equal to 0. If ZL, which is the impedance of the line, goes to infinity, then the reflection becomes 100% plus 1. Why? Because in such case, it means that you have an open circuit at the end or the termination of the line instead of a charge, okay? So the charge might have disconnected from the line. So you have an open circuit with a resistance ZL or an impedance going to infinity. So the entire signal that is incident would be reflected back. 100% of the incident voltage would come back with no consumption at the termination. That's why the reflection coefficient becomes plus 1. As for the short circuit, so if you have a short circuit in the middle, that would be the opposite of an open circuit. In other words, you have a short circuit behind the charge. So the signal would never get to the charge. In such case, the reflection becomes minus 1. ZL is equal to 0. Reflection becomes minus 1. But in all cases, the entire signal that had gone would come back, inverted here in such case. VSWR or voltage standing wave ratio. Another name for that, variable standing wave ratio. So voltage standing wave ratio or VSWR is a measure of impedance mismatch and is defined by VSWR is equal to V max divided by V min, reflecting the impedance mismatch between the charge and the line. It can also be expressed in terms of the magnitude of the reflection coefficient. So it is given by, and by the way, it's always a value greater or equal to 1. So VSWR is equal to 1 plus key divided over 1 minus key. So if the reflection is 0, then VSWR would be equal to 1. So VSWR is equal to 1 for perfect matching between the impedance and the line. If VSWR is equal to infinity, it means what? You would have the reflection coefficient would be 100%. So you would get 2 divided by 1 minus 1, which is 0, infinity. In such case, you would have full reflection and VSWR would be infinity. To put it in a different way, Vmin in such case would be 0 in front of Vmax. Standing wave patterns. The total voltage on the transmission line is the sum of the incident and reflected waves, given by V of x is equal to V plus exponential of minus j beta x plus V minus, which is the reflected wave, a j beta x, with beta is the constant of propagation constant. Factoring, so V of x is equal to V plus times e minus j beta x plus k e j beta x. The magnitude of the voltage varies along the line, forming standing waves. So V of x is equal to V plus multiplied by 1 plus k, which is the reflection coefficient, times e j2 beta x. As a reminder, beta is the phase constant, not the propagation constant. Maximum and minimum voltages. Vmax is equal to V plus, an absolute value, multiplied by 1 plus k, which is the reflection coefficient, also an absolute value. So even if it's negative, you need to make it positive. V minimum is equal to V plus multiplied by 1 minus absolute value of the reflection coefficient. The distance between successive maxima or minima is given by lambda over 2. That would be the distance. Power reflection and transmission. The incident power, P inc, is equal to V plus square divided by 2Z0. Reflected power, P reflected, is equal to K square times P inc. K, of course, is the reflection coefficient. Transmitted power would be the difference between two. The P inc, the P incident, minus the P reflected. So P transmitted is equal to the power of the incident wave minus that of the reflected wave is equal to the power of the incident times 1 minus K squared. Power reflection coefficient is given by reflectance is equal to K squared. Return loss. Return loss RL measures how much power is reflected back expressed in decibels. So RL is equal to minus 20 log base 10 K. Alternatively, it can be written as 10 log base 10 of the power of the incident wave divided by that of the reflected wave. Interpretation. High return loss, so you would have a low reflection, a good adaptation or matching of the impedance, in other words. Low return loss, meaning that you have a high reflection. Why? Because the loss is low at the return signal, so you have a high reflection and poor matching of the impedance at the end of the line. Exercise in reflections and standing waves. A lossless transmission line with characteristic impedance Z0 equal to 50 ohms is terminated by a load impedance ZL is equal to 30 plus J 40 ohms, where 30 of course is the real part, the pure resistance of 30 ohms, and 40 is the positive reactance. The line is excited by a sine source at a frequency such that the wavelength on the line is lambda. Okay, so you can write these questions down. Calculate the reflection coefficient KL at the load. Determine the VSWR or voltage standing wave ratio. Find the normalized load impedance, lowercase zl. Then determine the positions of the first voltage maximum and minimum from the load in terms of lambda. And finally compute the ratio Vmax over Vmin and verify consistency with the VSWR value. You can pause the video, try to solve it. Now let's jump into the solution. So the reflection coefficient, as you know already, based on the formula, is KL is equal to ZL minus Z0 divided by ZL plus Z0. Okay, so ZL minus Z0 divided over ZL plus Z0, which is ZL is 30 plus J40 minus Z0, which is the characteristic impedance, 50, divided by 30 plus J40 plus 50, equal minus 20 plus J40 divided by 80 plus J40. Now we need to remove the complex or the imaginary part from the denominator, so we need to multiply by the conjugate in the denominator, which is 80 minus 40J. We multiply both the numerator and denominator with Z value to get rid of the imaginary part in the lower denominator. Multiply numerator and denominator by the complex conjugate of the denominator, as we mentioned. So we multiply by 80 minus J40, both numerator and denominator. The denominator becomes 80 squared plus 40 squared, which is 6,400 plus 1,600, or 8,000. The numerator is minus 20 times 80 plus minus 20 times minus J40 plus J40 80 plus J40 times minus J40. So you can run the numbers. We get eventually J times 4,000. So KL is equal to J 4,000 divided by 8,000. You reduce the three zeros, both in numerator and the denominator. You get 4 over 8 is 1/2, which is 0.5 J. Now, as for the magnitude, because as we know already that for the reflection coefficient is a complex number that has a magnitude and an angle, a phase, okay? Now, the modulo or modulo is square root of 0.5 square, okay? Which is only the imaginary part because the real part is 0. So it's equal to 0.5. As for the phase, it is 10 of 0.5, which is, the imaginary part divided by the real part. That would be 90 degrees, okay? Because it goes to infinity. So it is 1 over 0, correct? So 1 over 0, which is 90 degrees. Because sine pi over 2 is 1 divided by cosine pi over 2, cosine 90 degrees, it is 0, as we know. And this is 10 alpha, it is 1 over 0. So since we have infinity, it is 90 degrees. The angle is 90 degrees. Now VSWR, or voltage standing wave ratio, this value is always greater than or equal to 1, by the way, okay? So it is equal to 1 plus key divided by 1 minus key, as we've seen here, which is 1 plus 0.5 divided by 1 minus 0.5 is equal to 1.5 divided by 1/2, or 0.5, equal 3. Normalized load impedance. Okay, what is the normalized load impedance? We simply divide ZL by Z0. So it is 30 plus J40 divided by 50, and we separate it into real parts and imaginary parts. So you get 30 divided by 50, which is 3 over 5. So 30 over 5 is 6. 3 over 5 is 0.6, okay? Plus 40 over 50, which is 4 over 5. So it would be 0.8, because 40 over 5 is 8. Here, 4 over 5, you need to divide by 10 also. So it is 0.8 J. Now, the positions of voltage maxima and minima. Voltage maxima occurs when the angle is equal to 0, and minima for an angle of 180 degrees. 180 degrees rotation. The reflection coefficient along the line is given by TL exponential of minus j to beta z. Beta is equal to 2 pi divided by lambda, the wavelengths. At the load, TL is equal to 90 degrees already. So 90 degrees minus 2 beta z is equal to 0. Then 2 beta z is equal to 90 degrees, equal pi over 2. Z then, in such case, is equal to pi over 2 divided by 2 beta. Okay, pi over 2 divided by 2 times beta is 2 pi over lambda. That's the phase constant, equal to lambda over 8. Voltage minimum is equal to or given by 90 degrees minus 2 beta z, instead of equal to 0, it should be equal to 180 degrees because we need to turn 180 degrees. Equal to, or then you have 2 beta z is equal to minus 90 degrees because this 90 is removed to the right handle of the equation, which is equal to minus pi over 2. Then z would become equal to minus lambda over 8. Since distance is measured toward the generator, the first minimum occurs at z is equal to 3 lambda divided by 8. The reason is z is equal to lambda over 2 minus lambda over 8, which gives us 4 lambda minus lambda over 8, or 3 lambda over 8. That's why. Voltage ratio verification, so it is given by Vmax divided by Vmin. That's VSWR. It should be equal to 3. So Vmax over Vmin is equal to 1 plus key divided by 1 minus key. It's equal to 1.5 divided by 0.5 equal 3. So if we get Vmax divided by Vmin, you will also have the same answer, which is 3, which is the VSWR value. Vmax divided by Vmin, of course, has to be 3, so that our calculation is correct. Vmax over Vmin is equal to 3 lambda divided by 8 over lambda over 8. So lambda over 8 and lambda over 8, both in the numerator and the denominator, can be redacted, and you remain with 3, which is the correct answer or correct value for the VSWR. Finally, impedance mismatch leads to reflections characterized by key. Standing waves result from interference of incident and reflected waves. VSWR quantifies the severity of mismatch. Power reflection depends on key squared. Return loss provides a logarithmic measure of reflection efficiency. Chapter 4, the Smith chart. The Smith chart is a powerful graphical tool used in RF and microwave engineering to analyze and solve problems involving transmission lines to get reflection coefficient, VSWR, and other parameters. Okay, so it is also involving or used for impedance matching, wave reflections. It provides a visual representation of complex impedance and reflection coefficients. Complex impedance normalization. Now you see, in order to use the Smith chart, we need at first to normalize the impedance, which means that, let's say you have a charge R having an impedance ZR, we need to normalize that by dividing the entire impedance with the characteristic impedance so that we can get values that are plotable on the Smith chart. We're going to see what do I mean by that. So at first, you need to divide the impedance with Z0. All right? So let's say the impedance was capital R plus J capital X. It becomes lowercase r plus J lowercase x, which is the normalized resistance or the real part of the impedance plus J times the normalized reactance, which means that after we had divided them by the characteristic impedance Z0, we get a normalized impedance that we can now draw on the circles of the Smith chart. So Z is the normalized impedance with normalized resistance R and reactance X. Similarly, we can normalize the admittance. Admittance is the inverse of the impedance, defined by Y is equal to capital Y over Y0 equal G normalized conductance plus JB normalized susceptance, which is the inverse of reactance, okay? And Y lowercase is the normalized admittance in such case. Mapping between the impedance and reflection coefficient. So the Smith chart is based on the relationship between normalized impedance Z and the reflection coefficient key, which we're gonna examine how to find that value, the value of reflection coefficient and even the VSWR on the chart. So key is equal to z minus 1 divided by z plus 1. Conversely, z is equal to 1 plus key divided by 1 minus key. This transformation maps the entire complex impedance plane onto the unit circle in the key plane, where key, the reflection coefficient, is a value less than or equal to 1. Smith chart structure. So the Smith chart consists of a set of circles and arcs representing constant resistances and reactances. The constant resistance circles, R is equal to constant, they are the circles that are centered by the horizontal axis. Okay? So you have the horizontal axis on the chart, we're going to see that. The center of these circles, or the centers of these circles, are placed on or localized. They exist on the horizontal axis. Constant reactance arcs, x is equal to constant. So on these circumferences, okay, on these curves, you have x would be equal to a constant. X would be a constant, and r would change as we rotate. Arcs intersecting the resistance circles. So key points on the chart. For the center, you have z is equal to 1. So it is a matched condition where key is equal to 0. The reflection would be 0. Rightmost point where you have, okay, to the right all the way, you would have an open circuit with coefficient of reflection is equal to 1, plus 1, which means 100% reflection. Leftmost point on the chart that we're going to see in a moment, on that you would have a short circuit where key, or the reflection coefficient, would be minus 1. Okay, so on this first Smith chart representation, you see here, on each of these circles, you would have a constant resistance, which is the real part of the impedance. Okay, so whenever you have a point on this R is equal to 0.2, it would always have, as long as it remains on this circumference, it would always have R equal 0.2 as a resistance, which is, in other words, the pure or the real part of the impedance. Okay? Here, for all of the impedances that are on this circle, they would have R equals 0.6. Here, for the circle passing with the center or through the center of this chart, for all the points here, they have the same resistance. Again, the real part of the impedance equal to 1. Here 1.4, here 4. Now, for these, you see these curves here, okay? Here, on these curves, the reactance would be the same throughout each of these curves. And by the way, for the upper part, upper disk part, the reactances would be of positive value. For the lower part, the reactance, let me draw that. So you see these curves here. The reactances, okay, on each curve would be the same reactance value. Okay, so let's say here it's not visible. I cannot see it, okay, but it would have the same reactance X. Normalized, of course, on every curve, but for the lower disk, again, for the lower part, the reactance values are always negative. For the upper part, here, for example, the reactance would always be positive. And if we've taken one curve, the reactance X would be constant on that curve, throughout that curve. Now, when we are plotting an impedance, so you would have an X value and an R value. So for example, here, it is R plus X, which is 0.2 plus X, whatever this X is. So the point would be here for Z, the normalized impedance, okay? And a final note, if you want to recover the original impedance value, you can multiply back the resistance and the reactance that are or have been normalized by the characteristic impedance. Another representation here to give you a clearer picture. So let's say an impedance value after normalization, it became 0.2 plus j times 0. Okay, so the real part is 0.2, the imaginary part is 0 for the impedance. All right, so how do we plot that? Now, for the real part, the resistance R, that would be the value. You need to read the value on this diameter. That is cutting the entire disk or Smith chart in the middle. Okay, so it is 0.2, this is 0.2. Now, since the impedance is sitting on the diameter, the value reactance for that would be 0. Okay, so except for the upper curves or the lower curves, the value of the reactance is always 0. Now, for the upper curves, the reactance is always positive. For the lower disk, lower middle of the disk, the reactance is always negative. So you have here 1 minus j 0.5. Here you have 0. Okay, why is it 0? Because here the resistance is 0. If you plot it all the way to the upper value, cutting the upper value, that would be 0. Now, minus 1.6, why? Because we've read it here somewhere, okay? So this would be minus 1.6, okay? If you can read it, that would be minus 1.6, and it would be the same throughout this curve, okay? The same reactance value. Here, we're gonna get to these later, how to measure the VSWR, the reflection coefficient, okay? In later slides. Constant resistance and reactance circles. So starting from the reflection coefficient, K is equal to R plus Jx minus 1 divided by R plus Jx plus 1. Separating real and imaginary parts leads to circle equations. This is how the Smith chart was drawn. Okay, so for the constant resistance, R K minus R divided by 1 plus R squared plus I K, so this is the real and imaginary part, is equal to 1 divided by 1 plus R squared. Constant reactance is given by this equation. Okay, no need to understand completely how we got that. Not we, but the one who found out these relationships, which is Smith. Okay, so the constant reactance X is given by R K minus 1 squared plus I. I would be the imaginary part. K minus 1 divided by X squared is equal to 1 divided by X squared. These equations define the geometric structure of the Smith chart. Admittance Smith chart. Okay, the admittance is the reciprocal of impedance or the inverse of impedance. So Y normalized is equal to 1 divided by Z normalized. Or Y is equal 1 divided by capital Z, the unnormalized value. On the Smith chart, admittance is obtained by rotating the impedance point by 180 degrees. So you need to reverse it by 180 degrees to get the admittance. Okay? Because it is the inverse. In other words, you need to turn it like this to the exact opposite pole. All right? This is how you get the admittance. So you reverse it by 180 degrees, which is a distance of lambda divided by 2. Okay? Half a wavelength around the center. Ky is equal to minus Kz. So the reflection of the admittance is minus the reflection of the impedance. Thus, impedance and admittance are represented on the same chart, simplifying analysis. Impedance transformation along a transmission line. The impedance at a distance L from the load is given by Z of L is equal to Z0, which is the characteristic impedance, multiplied by ZL, the impedance of the load, plus JZ0 tan beta L, with Z0, of course, the characteristic impedance. Beta is the phase, correct? Multiplied by L, which is the distance, divided by Z0 plus JZL tan beta L. In normalized form, Z of L is equal to ZL plus J tan tangent beta L divided by 1 plus JZL tangent beta L. On the Smith chart, this corresponds to a rotation along a constant key circle. Key property, key is equal to a constant along the line. Reflection visualization. The Smith chart directly represents the reflection coefficient. Key is equal to key in absolute value times E or exponential of J theta. Radius is equal to key magnitude of reflection, okay, in absolute value, and we're going to discover how to get the magnitude of the reflection and the angle or phase of reflection, okay? So theta is the phase of the reflection, and key in absolute value is the magnitude, just like any complex number, okay? Magnitude, you can say, is the square root of the real part square plus the imaginary part square when we're talking about a complex number. But graphically, we're going to discover how to actually measure that. Thus, distance from the center is the reflection magnitude, and the rotation, that would be the phase shift along the line or the angle of the reflection. VSWR determination. The magnitude of the reflection coefficient determines VSWR here analytically, but we can graphically also determine that. So VSWR, or voltage of the standing wave ratio, is given by 1 plus key divided by 1 minus key, with key is the reflection coefficient. On the Smith chart, VSWR corresponds to circles centered at the origin. Okay? These are called constant VSWR circles, so which are centered at the origin of the Smith chart. Okay, we're gonna see that. So maximum and minimum voltages now, again, they are called constant VSWR circles that we're gonna see, and maximum and minimum voltages are given by Vmax is equal to V plus, which is the incident wave voltage, times 1 plus key. V minus is equal to V plus multiplied by 1 minus key. Applications of the Smith chart. Impedance matching. So it is used to design matching networks by moving along the chart to reach the center where Z is equal to 1. Second, impedance transformation allows visualization of how impedance changes along a transmission line. 3. Reflection analysis, so directly provides magnitude and phase of the reflection coefficient. We're going to see how. And VSWR estimation, which enables quick determination of mismatch severity. Usually, the resistance and reactance are normalized in respect of the characteristic impedance ZC. This is the first thing that we do. We divide the impedance with the characteristic impedance. So the impedance of the charge, ZL, with the characteristic impedance of the line ZC, or you can call it Z0, so that they can be used in the Smith chart in order to evaluate stationary waves, S or VSWR, in other words, S parameter, and the coefficient of reflection, which is key or rho. So R normalized is given by R divided by ZC, and X or reactance normalized, that would be lowercase x rather, is equal to X divided by ZC. The normalized impedance has its origin to the extreme left edge of the outermost diameter, okay? As for the farmost edge to the right, that would be representing the infinite impedance infinity, okay? On the middle axis, splitting the chart to the upper and lower mid-circles that we've spoken about moments ago. The reactance on that diameter on that middle axis, splitting the chart into two upper and lower discs respectively. Okay, upper and lower mid discs, half discs. So on that, the reactance is null. On the upper circle, the reactance has positive values, but on the lower, it has negative values. As for the resistance, the real part of the impedance, in other words, is now on the external circumference, which is all the way to the left of the chart. Okay, so that would be a short circle, and it has a value of 1 at the center of the chart, at the middle of the circumference. This is the point where R divided by ZC would be equal to 1. Example, localization of a complex impedance. You have ZR is equal to 5 plus J 25. Characteristic impedance of the line is ZC is equal to 50 ohms. So how do we plot that impedance? At first, we need to normalize ZR. So lowercase zr is equal to zr divided by zc. So you divide it entirely by 50, which is the characteristic impedance. We get 5 plus j 25 times 25 divided by 50 is equal to 5 divided by 50 or 0.1 plus j times 25 divided by 50 or 0.5. Starting from the left extremity of the external circumference, we need to spot the intersection with the circle corresponding to a normalized resistance of 0.1. Okay, so you need to look at the circle that is crossing 0.1. Okay, the reactance circle cutting through 0. Actually, yeah, you have the circle of the pure or real part of the impedance crossing 0.1. So all of the resistances at that circle would be 0.1. And you need to also intersect it with the reactance circuit of, or a circle or circumference or curve rather of 0.5. So by following the circle in the upper section, since the upper section corresponds to positive reactances, they both intersect at point A. And we're going to see this point. So here it is. You have, first, this is 0.1. Okay? This is 0.1. And you start going upward. Now, where is the reactance that is positive 0.5? Here are the reactances. All right, so you have, if you can see it, okay, so you have 0.6, 0.7, okay, 0.8, etc. So this is 0.5, this curve over here. And where does it intersect with the circle, which is corresponding to 0.1? This is 0.1 over here, okay? It cuts here, okay? It cuts over here. So you draw the circle, and by the way, the wavelengths, okay, or yeah, how much wavelength that it would be distance. So for example, 0.5 lambda, etc. That would be read here. But for the reflection coefficient, it can be measured in two ways. So you either measure the distance from here to here, which is the radius of the circle. Let's say the radius of the circle is radius, and you divide it by the entire radius of the Smith chart, which is from here all the way to here. Okay, full radius. Or you can take the radius and place it on the reflection coefficient, okay, ruler, which is to the lower side of the chart. So that would give you a certain value. Of course, here I had to magnify it. It won't be accurate, but I can tell you it is a high reflection. It is almost 0.7. Okay? Yeah, exactly. 0.7 or 70%. Now VSWR or variable standing wave ratio calculation. So the evaluation of VSWR S factor, let's say we have a charge ZR is equal to 50 plus J times 35, okay, or a load rather. The characteristic impedance is ZC is equal to 50 ohms. So R here represents a charge or a load. First, we, as usual, normalize ZR, so we need to divide it by ZC in order to localize it on the chart. So ZR, lowercase, is equal to ZR divided by ZC equal 50 plus J 35 divided by 50 equal 1 plus J times 0.7. Then, using the compass, we trace a circle starting from the center of the chart, outer circumference, and intersecting with the impedance point. Every impedance located on that circle will have the same VSWR value, which is the voltage standing wave ratio. The VSWR is evaluated by measuring the same distance of this radius from the center of the lower ruler. Okay? So we measure it from the center of the ruler corresponding to the VSWR, okay, or right at the midsection of the chart, which is the diameter cutting the chart disk into two upper and lower half disks, you can also spot the VSWR value on that, okay? And where it intersects with the VSWR ruler, we read the corresponding value. Now, in order to plot it, remember at first that it was Z is equal to 1 plus J 0.7, the normalized impedance. So, where is the resistance that is equal to 1 on the chart? That would be the circle crossing the center of the chart. You see the center here? You see 1? If it's not visible, okay, this is the circle that corresponds to R equal 1. This entire circumference here, okay? Now remember that every impedance located on that curve has a resistance value equal to 1. Now, for the reactance, which is 0.7. So where is 0.7? First, it is positive, so you need to look at the upper midsection of the disk or the chart. You see here 0.5, 0.6, and 0.7. You see 0.7, so you go down all the way, and it cuts here. So this is the impedance ZC. Okay, so I will write it in green. So ZC is over here. It's not even visible. I'll try to use a different color. This is the impedance. Now, in order to get the VSWR, you need to trace the circle starting from the center of the chart all the way to the impedance, which is over here, okay? So, then you take the compass, and with the same distance, you keep the radius, you go to the ruler, which should have been located below the chart, but since they won't fit on this slide, I had to split them into two pictures. So you draw that same circle from the center here all the way, and you see where it cuts the VSWR ruler. You read here VSWR, correct? Can you see SWR? So let me erase here a little bit. Here you have a VSWR value of 2 in case you're not able to see it. So it cuts at VSWR equal 2. This is the variable standing wave ratio for this impedance. And when we spoke about the admittance, by the way, that would be 180 degrees far from the impedance. So it would be located on the other side, which would be here. That would be Y. Okay, and you can read the values for that by matching, okay, where it would have the radius and the reactance for it. Okay? It is 180 degrees far from the impedance, which is located in the above part circle. Another method is to measure the radius of the circle, which is the intersection of the circle with the Smith chart diameter. So for ZR in this example, the circle cuts the diameter at 2. So VSWR is equal to reflection coefficient, rho calculation. Evaluating the reflection coefficient for a charge ZR equal 150 plus J times 100 with characteristic impedance ZC is equal to 50 is done in the following way. Same way. First, we need the normalization by dividing ZR over ZC. So lowercase zr is equal to ZR capital over ZC equal 150 plus J 100 divided by 50 equals 3 plus 2J. Then you plot the circle corresponding to the charge on the chart. We need at first to localize the impedance on the chart. So what you have is 3 plus 2J, correct? Let's start with the real value, which is 3. We need to read that on the diameter. Starting from 0, which is the short circuit, all the way to the left, to the most left of the chart, you need to count, okay, here 0 0.1, 0 0.2, 0 0.3, all the way, okay. Here to the center you have 1, then you have 2, you have 3. This is 3, okay? You see the red circle here? This is R equal 3 on this red circle. Now, R plus 2J. Okay, where is 2J? First, it is a positive reactance, okay? And can you read here 2? This is 2. And on this curve, all of the impedances that would be located on this curve would have a reactance, normalized reactance, of course, of 2. So you go all the way down until you intersect with the red circle, and we get here to this red highlighted rectangle. Okay, this is the one corresponding to 3 plus 2J. Now, you need to plot the circle starting from the center of the chart all the way until it cuts with the impedance. Okay, and this same radius, you need to divide it by the full radius of the chart. This is how you get the reflection coefficient. Or you can actually measure it on this here. Okay, so you get the radius, distance, and you start from this origin here. This is the one corresponding to the reflection coefficient. Okay, so it gets all the way to here. Okay, this is 0.63, which is the coefficient of reflection. Now, it has another component, which is the phase or the angle. How do we get that angle in degrees, by the way? You simply read the value on the chart. Okay, so you see how. Because we need to draw a line from the center of the chart, which is this, all the way to Z. And notice where it cuts here. Okay, you have 10 degrees to 20 degrees. Each quadrant here is 2. So 12, 14, 16, and this is 18. Okay, this is 18. So it is 18 degrees. I hope it is clear. So again, let me try to clean it a little bit. You have 10, 12, 14, 16, and 18 degrees, exactly 18 degrees. So the angle is 18 degrees. As for the magnitude of the reflection coefficient, as we mentioned before, it is either given by observing here like measuring the distance or the radius on this ruler, it gets to 0.63, or dividing the radius length, okay, of this blue circle over the full radius, which is the radius of the Smith chart from here all the way to here. You get the same value, which is 0.63. Again, using the same radius distance, we place the ruler on the reflection coefficient line, or ruler below the chart, and we see where it cuts. In this case, it cuts at 0.63, so that would be the reflection coefficient. Another method is to get the ratio between the radius on the chart, okay, the radius of this circle that we've drawn that intersects with the impedance, and we divide it by the radius of the chart itself. So the ratio between this radius and the chart's radius gives us also the reflection coefficient. That would be another method, same results. The reflection also has a phase component found by measuring the angle formed between the line, okay, so you get the intersection, rather, of the line coming from the center of the chart, cutting through the impedance, and you follow it all the way through until it cuts the angular iterations around the chart. Okay, so where it cuts, you get the angle value. That would be the phase of the reflection. In this case, it is 18 degrees. In the above, we have a lossless line with a characteristic impedance Zc is equal to 70 ohms, connected to a receptor Zr equal to 115 minus 80J. Of course, 115 is the real part, that's the resistance, and the reactance or imaginary part is minus 80J. The wavelength is given by lambda is equal to 2.5 meters. Okay, so evaluate the standing wave ratio, VSWR, also Zmax, Zmin, distance to the receiver at the first node. Then, given that the power is 50 watts, okay, it's not showing up here. So evaluate Vmax, Vmin, V maximum, V minimum, Imax, Imin, and VR at the receiver. You can pause the video and attempt to solve it for yourself. Okay, then we will move on. So at first, we need the reduced impedance, Z, lowercase zr, or the normalized impedance, in other words. It is given by Z, R capital, divided by Zc, which is the characteristic impedance. So 115 minus 80J divided by 70, and it gives us 1.64 minus J times 1.43. As a note here, of course, 1.64 is to be found or traced at the middle axis, cutting the middle of the disk, the Smith chart. As for minus 1.43, it is to be found or traced on the lower part of the disk, which is the negative reactance part. So how do we localize the normalized impedance, lowercase zr, on the chart? Zr is equal to 1.646 minus 1.143J. We will start with the real part, which is the resistance. So if we look at the chart you have, and mainly to the central diameter of the chart, you have here is 1.0 ohms, which is the resistance of the impedance. Okay? To the left, you have 0.9, 0.8. Okay, we need to go to the right. So 1.1, 1.2, 1.4, 1.6, and 1.8. It is 1.646. So you have, by the way, the line between 1.6 and 1.8 is 1.7. So it is between 1.6 and 1.7, in the middle between these two curves. So this is where 1.646 should be. Okay, this red line. Now, it needs to cross with minus 1.43J. Okay, where is minus 1.143J? It is the negative reactance, which is at the lower middle of the chart. So you need to start from here. You have 1.2, 1.1, so 1.14, that would be this one. You go all the way up, and this intersects with the resistance, the pure resistance at this point, which is here, this point. After that, you need to trace the circle starting from the center of the chart O and intersecting with the lowercase zr impedance, okay? This would produce this circle where, if you read to the right, you get 2.7, which is the VSWR value corresponding to Z max. And to the left, if we read, it is 0.37, which is the VSWR value corresponding to the left side, corresponding to Z min. When we place the impedance on the chart and we draw the circle centered by O, we get VSWR is equal to 2.7 to the right and 0.37 to the left of the chart, the latter corresponding to Z min. Okay, now, when we draw a line starting from the center and cutting through the impedance, it intersects with 0.2 at the edge marker of the chart. So that would be 0.2 times lambda, or 20% of the wavelengths. Okay, so what would be the distance from to the first node? Okay, so since lambda is equal to 2.5, then 0.2 lambda equals 0.2 times 2.5 equals 0.5 meters. Let us evaluate Z min. Z min is equal to ZC times S prime plus 0J, okay, or divided by S, which is 2.5, okay? So Z min is equal to ZC times the VSWR value to the left, which is 0.37, so 70 times 0.37 equal 25.9 plus 0. Now going back to the chart, where have we found the 0.2 lambda that indicates the distance to the node, okay? So how have we figured that out? Because if you look at the chart, when we have traced the line starting from the center of the chart all the way crossing with or intersecting with ZR, it cuts the edge of the chart at 0.2 lambda. You see, this is the wavelength. Let me highlight it a little bit. So this is the wavelength, 0.2 lambda, where the line intersects with the edge of the chart, which is, by the way, this circumference is the marker of the wavelengths, or distances to the wavelengths. Now, as we travel a distance of lambda over 4, or 180 degrees, from the left to the right, the left being the VSWR equals 0.37, to the right where you have VSWR of 2.7, okay, which is corresponding to Z equals Z max. So the distance is 0.2 lambda plus lambda over 4, corresponding to the 180 degrees turn, gives you 0.45 lambda is equal to 1.125 meters. We get Z max is equal to SZC equal, S of course is 2.7 multiplied by ZC, characteristic impedance, 2.7 of course VSWR corresponding to Z max. So Z max is equal to SZC, just like the Z min is equal to S prime ZC, where S prime used to be 0.37. So it gives us 189 plus 0J. So we have Z min and Z max so far. Now let's get V max, the value for V max. Since we have the power, which is 50 ohms, and the formula relating the power with V max is P is equal to V max squared divided by Z max, which is equal to V max squared divided by S times ZC. So V max is equal to the square root of 50 multiplied by 189, which is Z max, is equal to 97.2 volts. V max is equal also to S times V min. So V min is equal to V max divided by S, 97.2 divided by 2.7 equals 36 volts. From V max and V min, we can easily derive I max and I min. So I max is equal to V max over ZC, which is 97.2 divided by 70, equal 1.4 amperes. I min minimum current is equal to Vmin divided by Zc, which is 37 divided by 70 equals 0.5 amperes. The current in the receiver is given by P is equal to RR I square. So 115 I square, which is RR, the resistance, which is the real part of the impedance, okay, times I square is equal to 50 ohms. So I is equal to the square root of 50 divided by 115, which is 0.66 amperes. Now, VR, the voltage at that impedance, is equal to ZR. IR equal 115 minus 80J times 0.66, which is the current, equal to, okay, here you get a complex number for which we can evaluate the modulo or the norm, the magnitude, and the angle. Norm is 92.46 and the angle is minus 34.82. So let us evaluate that. You have VR is equal to 0.66 times 115. 115 equal 75.9. Minus 80 times 0.66. So it is 52.8 J. Okay, so the square root of 75.9 square plus 52.8 square correct. This is, okay, 75.9 square plus 52.8 square gives us 92.458, so around 92.46. Now, as for the angle, which is the phase, if you will, that would be arctan or tan minus 1 of rise over run of the imaginary part, which is minus 80, divided by the real part. I'm sorry, not minus 80. This would be 52.8, okay? We multiplied the value. So minus 52.8 divided by 75.9. So again, shift tan of minus 52.8 divided by 75.9. Correct. This is minus 34.82. So we can write VR using this angular format, which is the norm of VR, 92.46, and the angle is minus 34.82. Now, as for the reflection coefficient, we can either get it graphically from the chart, or you can do rho is equal to VSWR minus 1 divided by VSWR plus 1 analytically, and you will get 0.324. Or another way is to get it from the chart. So you have in the chart, if you notice, you have the green circles that we've seen. Okay, you measure the distance or the radius for the green circle. You divide it by the radius R of the chart, the complete Smith chart. And this ratio would give you the reflection coefficient. Or you take that distance, lowercase r, and you place it on the reflection coefficient ruler, okay? And definitely you would get 0.32 if the radius gets to this point, okay, by distance. That will measure up to 0.32 reflection coefficient. Finally, the Smith chart maps impedance to reflection coefficient. It simplifies complex transmission line calculations into graphical operations, more handy, more practical. Key uses include impedance matching, okay, the uses of the Smith chart, what is it good for? Impedance matching, transformation and reflection analysis, and it is an essential tool in RF and microwave engineering. Chapter 5, Impedance Matching Techniques. Impedance matching is the process of designing a network such that the load impedance is transformed to match the characteristic impedance of the transmission line. This minimizes reflections and ensures maximum transmission, maximum power transfer from the source to the load. That would be like an antenna or another type of device. Importance of matching. When the impedance of the charge or the load is different than that of the characteristic impedance of the line, part of the signal becomes reflected. The reflection coefficient is given by K is equal to ZL minus Z0 divided by ZL plus Z0. So only when ZL is equal to Z0, then the coefficient for reflection becomes 0. So you would have no reflection at all coming back from the charge to the source. The transmitted power is given by P trans is equal to P incident power multiplied by 1 minus K square, where K is the reflection coefficient. Maximum power transfer in such case is when K is equal to 0. So P transfer becomes P inc, correct? This component becomes 0. More than that, if ZL is equal to Z0, then K becomes 0 here, okay? So with 0 reflection, you have maximum power transfer. This is when ZL is equal to Z0. The consequences of mismatch are reduced power delivery to the charge, signal distortion, and increased losses and heating. Quarter wave transformer. Okay, so a quarter wave transformer is a transmission line of length lambda over 4. So L is equal to lambda over 4. It is used to match a load ZL to a line Z0. Impedance of a transmission line is given by Zn is equal to Z0 times ZL minus JZ0 tan beta L divided by Z0 plus JZL tan, which is tangent beta L. For L equal lambda over 4, beta L becomes pi over 2. Okay? So what we get is Zn becomes equal to Z0 square, okay, divided by ZL. Correct? So basically, yeah, you have an inversion here and correct. So Zn becomes equal to Z0 square divided by ZL. Analytically speaking, and to make it more clear how we've gotten this answer, Zn is equal to Z0 square divided by ZL. So this is evaluated using a limit. Okay, let me clarify what I mean by that. So if beta L is equal to pi over 2, tan beta L, which is, by the way, it is sine beta L divided by cosine beta L. So it is equal to sine pi over 2, which is 1, divided by cosine pi over 2, which is 0. 1 over 0, infinity. Okay, so what would become the limit for that? These numbers become negligible, and you are left with Z0. So when beta L goes to infinity, when tan beta L goes to infinity, you are left with Z0 times JZ0 divided by JZL. J is reduced here, so we are left with Z0 square divided by ZL equal Zn. This is how we've gotten this answer. To achieve matching, Zn is equal to Z0, so Z1 is equal to square root of Z0 ZL, where Z1 is the characteristic impedance of the quarter wave section, which is the lambda over 4 section. Limitations, narrowband. So for narrowband frequencies, it would become frequency dependent and requires real valued load impedance. Single-stub matching. Single-stub matching uses a short-circuited or open-circuited stub to cancel relative components. Steps: normalize load impedance, which is ZL divided by Z0. Move along the transmission line to a point where Z is equal to 1 plus JX. Add a stub providing a negative reactance minus JX. Stub impedance, okay, Z stub is equal to JZ0 tan beta L, or for short-circuited stub, it is equal to minus JZ0 cotan beta L. Condition for matching, X plus X stub is equal to 0. Double-stub matching. Double-stub matching uses two reactive stubs placed at fixed positions. The advantages: no need to move along the line, easier physical implementation. Okay, so no need to move along the line, easier implementation. Method: first stub partially cancels reactance. The second stub completes the matching. Okay, so this is a double-stub matching in such case. The total admittance is adjusted to Y total is equal to 1 plus J0. Constraint: there exist forbidden regions where matching is not possible depending on stub spacing. Lumped element matching, L networks, used at lower RF frequencies where lumped elements are practical. Basic configurations: series inductor plus shunt capacitor, or series capacitor, so a series of capacitors plus a shunt inductor. So the inductor would be a shunt circuit, like a short circuit, but not short. It would be an inductance, okay, value circuit. Okay, so it would be like a circuit, but as you know, a short circuit, but as we know, at high frequencies, even the short circuit won't behave as a short circuit. So the dimensions, the lengths for the shunt would be the ones corresponding to a behavior similar to an inductor behavior. Same thing for the one above. It would be series of inductors, okay? Series inductor plus a shunt capacitor. So the shunt, like the short circuiting, that would be corresponding to a capacitor behavior. Reactances, XL is equal to omega L. XC, which is the capacitance reactance, equal to 1 divided by omega C. Design condition: transform ZL to Z0 using two reactive elements. Quality factor: Q is equal to square root of RL divided by RS minus 1, where RL, the resistance of the load, is greater than the resistance of the source. Component values: X series is equal to QRS, X shunt is equal to RL divided by Q, the resistance of the load divided by Q, which is quality factor. X series, the reactance for the series, is equal to QRS, which is the quality factor multiplied by the resistance of the source. Smith chart-based matching design. The Smith chart provides a graphical method for impedance matching. Procedure: at first, we need to normalize the load impedance by dividing it with the characteristic impedance of the line, which is Z0. So lowercase zl is equal to ZL, the original impedance for the load, divided by Z0, as usual. After that, we plot ZL on the Smith chart. Then we move along constant key circle, okay, toward the generator. We add reactive elements, series or shunt, to reach the center, okay? So Z is equal to 1 plus J0. So we move it all the way to the center. This is how we get the adjustment needed, reactive element values needed in order to adapt the impedance. Key operations: rotation, that would be the transmission line effect; radial movement, change in reflection coefficient, okay? Admittance conversion, that would be 180 degrees rotation, okay? Bandwidth considerations. Matching techniques differ in bandwidth performance. So we have quarter wave transformer for the narrow band, quarter wave, so lambda over 4. Stub matching, moderate bandwidth. for moderate bandwidths, you have stub matching that would be more appropriate, and lumped networks, for lumped networks, wider bandwidths depending on Q. Exercise: impedance matching techniques. A lossless transmission line with characteristic impedance Z0 is equal to 50 ohms is terminated by a load ZL is equal to 100 minus J50 ohms. You are asked to design a matching network so that maximum power is delivered to the load. Okay, we need to normalize the load impedance, determine the load admittance, design a single-stub shunt matching network, find distance from the load where the stub should be placed, determine the required stub acceptance. You can write down the questions, and briefly explain why impedance matching is important in RF systems. Normalized load impedance. At first, we need to normalize the impedance of the charge by dividing it with the characteristic impedance of the line, which is Z0. So lowercase zl is equal to ZL capital divided by Z0 equal 100 minus J50 divided by 50, which is 2 minus J times 1. This would be the normalized impedance that can be plotted on the Smith chart. Load admittance. The normalized admittance is given by YL equal to 1 divided by ZL equal 1 over 2 minus J times 1. Multiply the numerator and denominator by the conjugate, which is 2 plus J. So we get 2 plus J times 1 divided by 5 equals 0.4 plus J 0.2. That would be the admittance, which is the inverse of the impedance. And of course, it is normalized. Single-stub matching design. The idea is to move along the transmission line toward the generator until the admittance has a real part equal to 1. At that point, a purely reactive stub can cancel the imaginary part. So move to a point where the conductance is unity. Using the Smith chart or analytical methods also, we find that moving a distance of approximately 0.15 lambda toward the generator transforms the admittance to 1 plus J times 0.8, which is, by the way, adding 0.6 to the original admittance. So, add a shunt stub. To achieve matching, we need to cancel the imaginary part by adding a shunt stub of minus 0.8, which is the negative value of the current reactance of the stub. Stub length, okay, for a short-circuited stub, the normalized susceptance is B equal minus cotan 2 pi L. So, it is minus cotan 2 pi L. That would be equal to minus 0.8. So 2 pi L equal cotan. Okay, that would be the inverse of cotan, the arc cotan, so to speak, of 0.8. Numerically, cotan minus 1 of 0.8 is approximately 51.3 degrees. That's equal to 0.896 radians. Okay, so this is how we get the radian value. So you have 180 degrees is 2 pi, I'm sorry, it is pi radians, correct? So if we have 51.3 degrees, how much radians that would be? This would be 51.3 multiplied by pi radians divided by 180. This is how we convert from degrees to radians. So L is equal to 0.896 divided by 2 pi, approximately equal to 0.143 lambda. Final design stub position is approximately at 0.15 lambda from the load. Stub length approximately 0.143 lambda. Why impedance matching matters? That's part 4. In RF and microwave systems, impedance matching plays a central role in ensuring efficient power transfer and removing the reflection. When the load impedance differs from the line impedance, part of the signal is reflected back toward the source. This leads to reduced power transfer or reduced power delivered to the load, in other words, standing wave along the line, and possible distortion or instability in active circuits. By matching impedances, reflections are minimized to approximately zero, and the system operates at maximum efficiency. So again, for a small review, we had the admittance was y equals 0.4 plus 0.2j. We need to get it all the way to 1, correct? So that we can rectify or match the impedance. In order to get it to 1, you need to add to it 0.6, both on the real and the imaginary part. So you get 0.4 plus 0.6, 1. So it started becoming matched, plus 0.2 plus 0.6. This is 0.8J. After that, we need to remove the reactance so that we are left with y equal 1. That would be the adaptive impedance. So in front, or like for 0.8J, you need the negative value for that. That would be minus 0.8J. Okay, I'm sorry here. So minus 0.8, that is equal to B, which is minus cotan 2 pi L. So 0.8 is equal to cotangent of 2 pi L. So 2 pi L is equal to the inverse of the cotangent, cotan minus 1 of 0.8. So, which is, by the way, equal approximately to 51.3 degrees or 0.869 radians. So L is equal to 0.896 divided by 2 pi, which is approximately 0.143 lambda. Finally, impedance matching minimizes reflections and maximizes power transfer. Techniques include quarter wave transformers, stub matching, single and double, lumped element networks. The Smith chart is an essential design tool for visualization and solution. Choice of method depends on the frequency, the bandwidth of operation, and elementational constraints. Chapter 6, Microwave Components. Description: Microwave components are essential elements in RF and microwave systems used to guide, control, and manipulate electromagnetic waves at high frequencies, typically in the range of 300 MHz up to 300 GHz. Proper design and selection of these components is crucial and critical for ensuring low loss, high power handling, and desired impedance characteristics. Waveguides. Waveguides are hollow metallic structures that guide electromagnetic waves from one point to another. Unlike coaxial or microstrip lines, waveguides support transverse electric TE and transverse magnetic TM modes. Rectangular waveguide, the dominant mode is TE10 with cutoff frequency given by Fc is equal to C divided by 2A, where of course C is the speed of light in vacuum, and A is the wider dimension of the waveguide, of the rectangular waveguide. So you have like a section rectangular, okay, with a width and a height. The longer would be the width in such case. So Fc would be equal to C divided by 2W. The wave impedance for TE modes is given by ZTE is equal to Z0 characteristic impedance divided by square root of 1 minus Fc divided by F square, where Fc is the cut frequency. Z0 would be equal to 377 ohms, is the free space impedance. The advantages: you have low loss at high frequencies, high power handling. Applications for radar, satellite communications, and microwave ovens. Second, coaxial lines. Coaxial lines consist of a central conductor, the electric insulator, and outer conductor. Okay, the outer conductor would be the edge of this blue disc here. The dielectric is the blue color on the inside of this disk, and the conductor, the main conductor, which is the central conductor, is the one having lowercase d as a diameter. Okay, they are widely used for RF signal transmission due to their simple construction and shielding against electromagnetic interference. Characteristic impedance is given by Z0 is equal to 60 divided by square root of epsilon r, which is the relative permittivity of the dielectric, ln or logarithm of d capital divided by lowercase d, with d capital is the diameter of the outer conductor, okay? And lowercase d is the diameter of the inner conductor. Epsilon r is the relative permittivity of the dielectric. Applications: RF test equipment, antennas, interconnects in communication systems. Microstrip lines. Microstrip lines are planar transmission lines consisting of a conducting strip, which is, by the way, printed on a substrate. Just like you have electronic circuits that are printed. When you look, for example, at your motherboard of your computer, it is a printed circuit. In the same way here, you have printed antennas called microstrip antennas. These are planar transmission lines that are flat, printed on a substrate, and with a lower conductor, lower base on the substrate, that is actually the ground plane. So you have a plus, okay, a strip line on the upper part of the substrate, and you have a base ground on the lower part. These two, the plus and the minus, are separated by a substrate, which is the dielectric. They are extensively used in compact RF circuits. Characteristic impedance is given by Z0 approximately equal to 87 divided by square root epsilon r plus 1.41 ln 5.98 h divided by 0.8 w plus t, where h is the substrate thickness or the height of the substrate, w is the width of the strip, t is the strip thickness. Epsilon r is equal to substrate relative permittivity. Advantages: very easy to integrate with PCBs, low-cost fabrication. Applications: RF filters, antennas for mobile phones, and microwave circuits. Here to the right, you have a small illustration of what that microstrip line would look like. In this image to the right, you have a patch antenna, which is the microstrip. That would be like positively oriented. It would have a positive polarity, and the ground, the minus, the negatively charged conductor, would be attached to the ground, and between these two would run an electromagnetic wave, which would be the radiated wave from that antenna. Okay, the dielectric epsilon r having a relative permittivity. You see h is the thickness of the substrate, and w and l are the dimensions, width and length of the patch antenna. Also, t, which is the thickness of the microstrip line, should also be mentioned. Now, another thing to note is that when epsilon r is low, that would encourage or facilitate the radiation of the electromagnetic field to the outside, so this entire component would act as an antenna, not a filter. You see, the filter would have a completely different structure with an input here and an output, which would also be like a conductor here at the edge. Now, for a filter, the electromagnetic field should be kept on the inside of the substrate. So they would have a substrate with a high relative permittivity so as to keep the electromagnetic wave from being radiated to the outside of this substrate. Okay, so that we can push it to the outside from this interface, okay, because that would be working as a filter, like low pass filter, high pass filter, to only allow like a specific bandwidth to pass through, or a high frequency or high frequencies to pass through, while cutting the low frequencies. That would be the high pass filter. Or for the low pass filter, it would cut out the high frequencies and allow the low frequencies to come through from this interface. But we would not want, in such case, to have waste. So the permittive relativity would be very high so as to keep the electromagnetic wave from surging on the outside of the substrate. So it would be kept imprisoned within the substrate, and it would only gush out from the right interface in such case to go to the component that is receiving the low frequency or the high frequency. Directional couplers. Directional couplers are 4-port devices that sample a defined fraction of the power traveling in one direction of a transmission line. Coupling factor C is equal to 10 log base 10 P input divided by P coupled in dB. So this is like the antenna 3-junction, like a T shaped coupler for the antenna, where the signal can be distributed from the dish antenna to down to 2 receiving devices, such as 2 TVs instead of 1. Directivity measures the ability to isolate forward and backward waves, by the way. That would be equal to D equal 10 log base 10 power of the transmitted wave forward divided by power reverse in the CBOS. Applications: power monitoring, signal sampling, feedback networks. To explain further the concept of directivity, you have here this plot where we have for azimuth plane and elevation plane the radiation pattern, what is called the radiation pattern. Let me explain it for a second. So the radiation pattern means that in the azimuth plane, which is the horizontal plane, okay, the shape of the radiated wave is like this. It is circular, okay? It's not that perfect, actually. It should have side lobes, but they are minimal, and the side lobes would be considered as loss, okay? These are the things that are considered when we talk about the directivity. Now, this is more obvious when it comes to the elevation plane. In this example, the elevation plane is, this is the radiation pattern in the vertical direction, meaning that in the vertical direction, you have a primary lobe like this, and above it and below it, you have 2 secondary lobes, which are considered as waste. They don't participate directly in the transmission purpose. So they are surging to the right and to the left, okay? They are not intended to be broken from the primary lobe like this. Now, directivity is 10 log base 10 power of the transmitted signal that is pushed forward divided by the power of the reverse signal, which is the power of these 2 secondary lobes. That would be the directivity. So how much power ratio is there between the power of the main transmitted signal forward, which is the yellow upper lobe, divided by the power that is wasted sideways, both on the right and on the left. This is what gives us the directivity for the antenna in the vertical direction. Power dividers. Power dividers split an input signal into 2 or more outputs while maintaining impedance matching. Ideal lossless divider for an n-way equal divider, P out should be equal to Pn divided by n, which is how many outputs there are, 3 outputs. So the power at the output of each of these 3, ideally without loss, would be equal to the power of the input divided by 3. Okay, so the power would be divided equally among different outputs. Types: you have resistive, which is Wilkinson with isolation resistor. Applications: antenna arrays, measurement systems, phased array networks. Attenuators. Attenuators reduce the amplitude of RF signals without significantly distorting the waveform. They are used to protect sensitive components, improve matching, or control signal levels. Attenuation in dB is given by LdB is equal to 10 log base 10 power at the input divided by power at the output. This is how we measure the attenuation in the CBOS. Types: you have fixed attenuation, variable, P-pad, and T-pad. Applications: signal conditioning, measurement calibration, and power level adjustment. Finally, microwave components provide the fundamental building blocks for RF and microwave systems. Their proper understanding, design, and implementation are critical for achieving low loss, high performance signal transmission and processing. Chapter 7: Scattering Parameters, S matrix. Scattering parameters, commonly known as S parameters, are a fundamental tool in high frequency and microwave engineering. They provide a convenient way to describe how RF and microwave networks respond to incident and reflected waves. S parameters are especially useful at microwave frequencies where the voltage and current measurements are difficult, and power-to-wave relationships are more practical. Definition. So S parameters describe the relationship between the incident and reflected voltage waves at the ports of a network. For an N-port network, the general relation is B is equal to SA, where B is the tensor for the reflected waves at each port, okay, B1, B2, Bn, etc. A is the tensor or vector for the incident waves at each port, and S is the n by n S matrix of the network. Each S parameter, Sij or J, is defined as Sij is equal to Bi divided by Aj. This represents the ratio of the wave exciting port I to the wave incident on port J, assuming all other ports are terminated in matched loads. Reflected and transmission coefficients. So the reflection coefficient at port I is given by Sii. Okay, so key I is equal to Sii equal Bi divided by Ai. Okay, transmission coefficient, transmission from port J to port I is given by Sij. So Tij is equal to Sij equal to Bi divided by Aj. Remember that I is the reflection port and J is the incident port. Two-port network analysis. So for two-port networks, which are the most common in microwave circuits, their S matrix is given by S is equal to S11, S12, S21, S22. S11 is the input reflection coefficient at port 1. S22 is the output reflection coefficient at port 2. Okay? Now, S21 is the forward transmission coefficient from port 1 to port 2, 2 being the receiving. S12 would be the reverse transmission coefficient, which is from port 2 to port 1. Okay, so S21 is the forward transmission coefficient from port 1 going to port 2. S12 would be the reverse transmission from 2 to 1, from port 2 to port 1. For a matched network, S11 should be equal to S22 is equal to 0. No reflection at all, and S21 should be approximately equal to S12. Okay, forward would be equal to reverse transmission, approximately, less than or equal to 1. Measurement using vector network analyzer, VNA. VNAs are instruments designed to measure S parameters across a range of frequencies. They inject a known signal into the network, measure reflected and transmitted waves, okay, the reflected and the transmitted waves, and calculate S parameters. Key steps in measurement: connect the device under test, DUT, to VNA ports. Apply calibration standards to remove systematic errors. Measure incident and reflected waves at each port, and compute the S matrix from these measurements. The relationship to the Smith chart, S parameters, particularly the reflection coefficients S11 and S22, are directly represented on the Smith chart for impedance matching and network design. So key is equal to SII equal ZL minus Z0 divided by ZL plus Z0, where ZL is the load impedance and Z0 is the characteristic impedance of the line. Applications of Smith chart: visualizing impedance and admittance, designing matching networks, and determining stability circles for amplifiers. Scattering parameters, S matrix exercise. Consider a two-port microwave network operating at a given frequency. The measured scattering parameters are the following: S11 equals 0.2 and the angle minus 30 degrees. That would be the reflective parameter at port 1. Then at port 2, 0.3, angle minus 45 degrees. S21 equal to, and the angle 60 degrees. That would be the transfer from port 1 to port 2. S12 transfer from port 2 to port 1, which is the reverse, 0.05, angle 10 degrees. The reference impedance at both ports is Z0 equal 50 ohms. So you can write down the questions and try to solve it yourself before we get to the solution. Write the complete scattering matrix of the network, that's 1. Determine whether the network is reciprocal, that's 2. Check if the network is lossless. If port 2 is terminated with a matched load, compute the input reflection coefficient, key in, at port 1. Determine the transducer power gain, GT, under matched conditions. Okay, at first, the scattering matrix. So you have the first line, first two arguments are S11, S12. Okay, so the first argument is for the line number, which is the first line. Second argument is for the column. So S11 means first line, first column. Then S12, first line, second column. Then S21 and S22 are respectively second line, first column, and second column. As we mentioned before, S11, S22 are the reflection parameters, respectively at port 1 and port 2. As for S21, S12, they are the transmission parameters, respectively from port 1 to port 2. This is the incident wave, and here is the retro wave, the wave that is coming in the opposite direction from port 2 to port 1, transmission wave. Equals 0.2, phase angle minus 30, 0.05, 10 degrees to 60, and 0.3 minus 45 degrees. We actually copied them from the question. Second, reciprocity. Reciprocity means that S12 is equal to S21. The incident wave, the transmission from 1 to 2, is equal to the reflective wave coming from port 2 to port 1. If the port network is reciprocal. So is S12 equal to S21? Here S12 is equal to 0.05 and the angle is 10 degrees. S21 is equal to 2 and the angle is 60 degrees. So neither the magnitude nor the phase are matching. They are both different. Then the network is not reciprocal clearly. Lossless condition. For a lossless network, the S matrix must be unitary. One necessary condition is that S11 modulo the magnitude at S11 square plus S21 modulo square should be equal to 1. S11, by the way, is the reflection coefficient at port 1. Okay, modulo square plus S21 modulo square, which is the transmission from port 1 to port 2, should be equal to 1. Compute, okay, so S11 square is equal to 0.2 square, which is the magnitude of S11 square. If you look back at the value of S11 within the problem, so it is equal to 0.04. S21 square is equal to 2 square equal 4. Added together, it is 0.04 plus 4 equal 4.04, which is different than 1. Thus, the network is not lossless. In fact, since S21 is greater than 1, the network exhibits gain. It is active. Input reflection coefficient with matched load. When port 2 is matched, then key L, in other words, the reflection coefficient for the load is equal to 0. It should be equal to 0. So the input reflection coefficient becomes key N is equal to S11 plus S12, S21 key L divided by 1 minus S22 key L. Since key L is equal to 0, then key N is equal to S11. Okay, so this entire argument would be removed, which is 0 divided by 1. And that would be 0.2 with the phase angle minus 30. So key N should be equal to this value since the load is matched. Finally, the transducer power gain. Under matched conditions, both source and load matched. The transducer gain simplifies to GT is equal to S21, which is the power transmitted from port 1 to port 2, modulo square. That would be the gain of the transducer, okay? The gain of power. So it is equal to 2 square equal 4. Now in decibels, that would be 10 log base 10 of 4. So 10 log base 10 of 4 is approximately equal to 6.02 decibels, which is, by the way, a very powerful tool and method to convert it to decibel, because you would have a large gap at times between very low powers and very high powers. So the decibel value would keep it in check in order to make it more practical and more usable. Finally, S parameters provide a modern practical approach to characterizing high-frequency networks, facilitating analysis, design, and measurement without requiring direct voltage or current observation. They form the backbone of RF and microwave engineering. At the end, thank you for watching. Hope you enjoyed this series and see you next time.